Okay, all right, let's go ahead and get started. So let's talk about the final exam. So that will be that's scheduled for, I believe, next Friday at 8 a.m. Let me just check our schedule of classes. So here we are, Stats 21. Yep, okay, Friday, December 15th at 8 a.m. This is just as scheduled by the registrar's office, but it will not be taken in class. It will be taken at home. It's a coding exam, and so the way it will look. Let me see if I can get this thing to download, and we'll open it. Basically, it will be a similar format to kind of a homework assignment, in that I will post a Jupyter notebook, maybe any kind of supplemental data files, and you will download it and you'll work on it. And you've got 3 hours to get everything done and submit back onto, submit on Gradescope here. Okay. So you'll take it at home. I'm going to ask. I will send out a link with a. That you'll use, but I'm going to ask that everybody logs into Zoom, and this is just kind of a minimal form of proctoring, I guess, and it's mostly to kind of just ensure that you're working alone, you're not having like a final exam party where you're taking the exam together and working on the answers together or something like that, okay? It is at home online, and so I'm going to just leave it at as open note, open book. You can use notes I've created for this class. You have to kind of look at your own homework solutions. I don't want you to be passing, swapping homework solutions and things like that. I have links as far as Python documentation and things like that. You are also allowed to look up existing questions that already exist on places like Stack Exchange. Obviously, do not post questions from the exam, or don't ask somebody else for like, how do you do something here? Okay, so no collaboration allowed, and then of course, do not share the exam file. Don't post or distribute the exam file, anywhere. So. Yes, please log in on Zoom with your cameras on. If your laptop or your computer has problems with the camera, then an alternative that you can do is open Zoom on your phone, and you can use the camera on your phone as a way to kind of check in for proctoring. Okay. So that's how the exam will run. Are there any questions on that? So that will be so that's how we'll proctor the exam. And then as far as like what can you expect to see on the exam, I'm still kind of writing and tweaking this, but I think there's going to be kind of two major parts to the exam. One is going to be working with pandas and matplotlib to do some data manipulation, data summarizing, data visualization, right? So please, so you can look at, say, homework 4, where you did a little bit of work with pandas, but you can expect, a different data file. And different types of questions where you'll have to definitely kind of do a group by operation and find, what is the mean or the median of a certain group. You might have to do some pivoting, you might just have to do different kinds of operations, try to answer the question. So, you have data and I'll have questions kind of related to the data, and you'll you'll figure out the answers using pandas. I'll also ask you to create some visualizations with that. So that will be a big part of the exam. And then the other part of the exam, so here are just possible other things I've listed off. I'll ask you to do several tasks of the data, which could include any of the following things, such as changing the index or creating a date-based index, or re-indexing the data and filling in missing values or remove missing values, subset the data based on some criteria, group the variable based on group the data, I guess, based on a variable and calculate the mean or other summary statistics for each group, create a new column using calculations based on other variables, calculate correlations, create line plots, or create stacked or side-by-side bar plots. And basically, familiarize yourself with the different plots that you can do with a data frame. I've linked to some of the documentation. I imagine this will be very important that you're familiar with the documentation, okay? And an important part is being able to kind of read documentation for a new function that hasn't necessarily been taught to you, but that's going to be an important thing. Is like, can you read documentation and understand how a function works or gets applied? So I might very well ask you to use a certain function that I haven't explicitly covered in the class. I'll point out, like, I'll tell you what the function name is, but then you'll have to kind of read the documentation on the function and understand how to use it. So one thing you can do as far as studying and preparing, because you've got 9 days ahead of you to study, and I know there's a lot of other classes and you got other work and projects and things going on like that. But one thing you can do if you're looking for practice is just spend some time on the documentation pages. There's going to be a whole bunch of functions, whole bunch of methods listed, and see if you could try some of them out, right? Start off by kind of copying and pasting examples. You go on Google, type in like pandas, series, method name, whatever it is, and examples, and you'll find examples. Okay, you'll find examples. So that's I think a great way to kind of learn. And then after I ask you to do some of these summary operations, I might ask you just what's the interpretation on the finding there. Okay, so that's going to be a big part. And then the other part of the exam, outside of the pandas and the matplotlib and the plotting and all of that, I will ask you to write some code, write some functions, and define classes and things like that. So review the lecture on object-oriented programming regarding like creating classes and creating methods within your classes. And then also just review, if you need to, I would say especially the functions that I might ask you to write. So you'll have to, I guess review how to write a function if you need familiarity with that. But I think you at least know how to define functions and stuff. But the operations that I'll ask you to do will involve either strings, tuples, lists, dictionaries, these different kind of iterables, and things that you might have to do with them, right? Like if you have a list, review how to append values to it, or insert values, or pop things. With tuples, what are some of the different things that you can do? So I'll ask you to write a few functions that will take in arguments, perform some kind of task, and output something. A common thing I see students do is they use print statements rather than return. And so think about what the task is. And if it's asking you to calculate something, you're going to want to use a return, okay? Because print, all it does is it just outputs something to the screen. but that value is lost. It's not kept track anywhere. So you should be using return with a function in general. In general, you should be using return, unless it tells you to make sure you output something to the screen in some kind of way. But in general, you'll want to use return. And I said, these functions can cover a range of topics, but I especially recommend familiarizing yourself and reviewing, methods and attributes associated with strings, tuples, lists, and dictionaries. We've got lectures kind of covering each of those data structures in Python. And I'd say those are the most important ones. And then, regarding object-oriented stuff, I might have you define a class, and then within the class, you'll have certain methods, and I might ask you to use, some of Python's double-under, dunder methods, like, well, obviously init is vital, but also string, less than, add, length, get item, etc. We covered a handful of these dunder methods in Python classes here. Okay, so that's the plan for the final exam. Still kind of tweaking and finishing up the exam questions, but this is kind of what you can expect. All right. And I think the hardest part of all of this will be the time constraint. You'll have 3 hours, so we'll start at 8, ends at 11. That's the time we're scheduled. So you'll log in, and that will be that. And sometimes, as you're trying to figure out a solution, your brain just draws a blank or something, and so you work on different parts of the thing and then come back to that part, right? My suggestion, is just write some code, review the notes, and try writing your own things. Think of different tasks. Some students were asking, like, how can I study? So, you have access to DataCamp. Oops. Clicked the wrong button here. So you have access to DataCamp through March of next year. I think March 24th. I think it goes from September 24th to March 24th or something like that. Why is this not logging in? Okay, let me go to sign in. I need to sign in with this. And so if you go to learn, you have practice. So these are different things that you can do for practice. And then you also have projects, okay? And then under projects, you can find like little Python projects and, look at things like, I would say look at data manipulation projects and things like that. The guided ones kind of help you through it. You can also try an unguided one, but I'd say that can be a little bit tougher. But I'd say within DataCamp you have practice and you have projects, and I'd say those are good sources of practice if you want to try to kind of sharpen your skills. And I think it's I think this is a great resource, so highly recommend that you take advantage of the DataCamp subscription that's been provided to you generously through DataCamp. This is their premium product that if you were to purchase, it's quite expensive. I think, if during the summer or something you're like looking for ways to kind of sharpen your skills, I do recommend DataCamp, and I think it's worth subscribing for a couple of months. They always try to get you with like signing up for a full year and things like that, and that's a lot like the gym membership, where as soon as when you first sign up, you go there every day for a few weeks, maybe a couple months, and then it kind of drops off. And I think that's just human nature, right? Start of the next year, winter quarter, January, Wooden Center is going to be packed, okay? And then midterms come around, and then things start to drop off. But that's just how things go. But anyway, you have access to DataCamp. I think it's a great resource. I've assigned several chapters out of them. You can always kind of review those chapters as well. But that's what we have there. Okay. Any other questions regarding the final exam? No? All right. Okay. Well, then let's go ahead and take a look at today's lecture. Let me clear all of my outputs. So I was going to just introduce a little bit of stuff from sklearn. Today's lecture is going to kind of focus a lot on this concept of cross-validation and using, splitting your data between training and testing to kind of measure the performance. And I've done a lot of this stuff a little bit manually to kind of illustrate how this stuff works. This is not a machine learning course, so we're in this little awkward space where some of you have taken say 102B with me, where I cover some machine learning concepts. Others of you might have taken a machine learning course somewhere else, and then some of you, this modeling stuff is very kind of new, novel and unfamiliar. So, you know what? Let me give you your first view quiz answer before we even get started. Okay, so what we have, question one. Question one is C, I believe, yeah. Question one is C. All right, so the concept in statistical modeling is the idea that, in real life, we are gathering data, right? This is always the case, right? We live in the real world and we get data from some place. And so this data is generated by some kind of real world process, like how tall is somebody? There's a bunch of factors that go into determining how tall someone is. We look at their genetics, so the height of their parents, nutrition, their age, different kinds of factors, right? But you can have two siblings, same parents, similar nutrition, and as full-grown adults, they could be very different heights, right? Because I guess even after you account for the parents, there's still randomness, right? And maybe we could actually pull out their genetic sequence and figure out what genes are responsible for heights and things like that to get a finer thing. But basically, there's some real-world process that determines how tall somebody is. But we're not really interested in that real-world process. We just want to know, can I approximate how we get that number? Okay, we just want to model. We just want to create a simple model that just says, hey, you know what? Let's plug in a few variables. We'll plug in age. All right, if they're a kid, older kids are taller, younger kids are shorter. If they're an adult, then we're going to just assume full-grown thing. Maybe we'll throw in a few other factors, right? We'll put in gender, and we'll just say if somebody is is male, we'll just assume they're a little bit taller. If someone's female, we'll assume they're a little bit shorter. Of course, that's not going to apply universally. That's just general trends. We're just trying to capture general trends here. And then I don't know, other kinds of factors we can say. All right, how tall was your parents? What were your parents' average height? Okay, and we throw that in there, and we'll just say on average, if your parents were tall, then we're going to predict your height is taller, and on average, if your parents are shorter, we're going to predict you're shorter. And maybe we'll use those three variables: parents' average height, gender, and then age. And we plug that in, and we get just this simple model. All right, we say, okay, tall parents, full-grown adult male, we're going to predict this height. Okay, short parents, child, this, we're going to predict this height. But obviously, the actual data values aren't going to match exactly our predictions, so we always have to kind of include an error term. And so anyway, modeling is just like, can we come up with some set of either mathematical equations or some sort of system to just produce numbers, numeric outputs. And the goal is generally we want the numeric output that we produce on our computer or our model to be kind of close to the actual numeric value that we recorded in our data, right? And we say our model is good if our numeric prediction is very close to the actual value. And our model could use improvement if our numeric prediction is quite a bit different from the actual values. So the way we want to do this, though, is let's say we have all of this available data. We don't want to train our model using all of the data. Training here, what training means is figuring out like the slope and the intercept or the parameters or whatever, the system that you use to make your predictions. You might, if you use some kind of just like a linear regression model, that means you got to figure out what the slope is and what the intercept is, right? And you're going to get the line. And you might say, well, let's use all of the available data to figure out what our slope and intercept should be. The problem of using all of your available data is that you can always tweak your model so that your line fits your available data, your training data better and better and better. And then you can say, well, I did a great job. But how do you assess if your model is actually any good? Well, you don't have a way to do that. So generally what we want to do is we want to split our available data into a training portion. We use the training part to estimate our slope and our intercept, the model parameters, all of those terms. And then once we have that, we're going to assess how well does our model perform by using it on the testing set. Right here it says holdout sample. And we say, okay, here's data that I've never seen before. And let's see if we can make good predictions there, right? It's kind of like how well can you predict the future? Well, we can only really assess our ability to predict the future by making a prediction now and then seeing if that prediction comes true in the future. Okay, if we only just talk about like, oh yeah, I totally knew that this was going to happen, right? It's all in the past, and you just keep saying like, oh yeah, I already knew that all of these things would happen. It's hard to believe that all of that's going to be true. Okay, so anyway, we're going to import a few functions from scikit-learn. So sklearn is the package, but you're going to want to type in scikit-learn. I guess scikit is one word. This is kind of the most popular machine learning package, and there's there's quite a bit of stuff. It's divided into, say, classification, regression, clustering, dimension reduction, model selection, pre-processing, and things like that, okay? And there's quite a bit in the user guide for all of the different kinds of models that you can fit. So that's the documentation. But anyway, we're gonna import things from model selection. In particular, we'll import train test split, which is going to take our available data and split it into training and testing data. And then we'll also do some cross-validation. Now, once you split your data into a training and testing data, then while you are doing the training and you're modeling, part of the process is usually trying out different competing models. So when you do linear regression, you might want to say, well, what if I used father's height as a predictor variable? And then someone say, no, you should use mother's height as a predictor variable. Or someone else might say, no, you should use sibling height, right? And so you might have these different competing models that say that each of them use different variables, or you might say, hey, you know what? Let's try out a linear regression model. Let's also try out a random forest. Let's try out boosted trees. Let's try out different kinds of models that are available. Splines or things like that. And we're not going to cover all of those things today or anything like that. But within that, how do you assess your model performance? Well, you're going to further divide your training data into a training set and a validation set. Okay, so within the training data, you're going to further divide that. Some places call this the analysis set and the assessment set, but basically you take your training data and you further split that. So you use these kind of splits to help decide which model you like the most. And then once you have a model that you like, you can, at the very end, you test it against the testing data to see if the model is still high performing here. Okay. All right. So anyway, I just wanted to show you a little bit on how train test split works. Okay. And so first, I'm going to just start off with a very, very, very simple set of arrays here. So I have this two-dimensional array called X. Here I've got 10 rows and 2 columns. And then we're going to have kind of just a numeric array for Y. And then I'm also going to have another array Z, and this is going to be categorical. I've got zeros and ones here. Okay. So what train test split will do is you can put in some kind of matrix array, whether it's one-dimensional or two-dimensional, and you specify what proportion of your values you want to keep in the test set. So in this case, I'll say my test size, I want 1/4 of my values. And then you can do random state. You specify the random state so that, because what it will do is it's going to randomly select rows out of here. And if you want to be able to reproduce these results and reproduce, the random selection here, then you specify the random state here. So here I'm going to take X, my two-dimensional array X, and what it will return is it will split X into a training set and a test set. And so I'm going to unpack that, do tuple unpacking, and I'll print out X train and X test. And so we can see out of the, there were 10 rows. And so I said I want 1/4 of my rows to go into my test set. And so it just says, well, the best I can do is 30%, right? So out of 10 rows, it puts 3 in my test set, and it puts the other 7. And then the rows that it selected were rows 4, 0, 3, 1, 7, 8, 5, 2. And then for the test set, it put rows 2, 9, and 6. Okay, so it just kind of randomly selects these things. If we want to also split the Y the same way, then we basically put in y here, and we with the same arguments. And here I got to choose the same random state, otherwise it's going to select different rows here, right? So with y, it selects values 2, 9, and 6 for the test, and values 4, 0, 3, 1, 7, 8, 5. And we can see that this matches up, right? Because here on my x, I had rows 0 through 9, and then for y, I have the same values 0 through 9. And we can see that, this matches up. Now, if I change the random state, we would get completely different values, right? Random state 2 gives me different values, but I could kind of have this match up using random state 2, and we would get the same kind of thing. So, by specifying what random state you want, you can kind of make sure your results are reproducible, which will be important. Okay. Now, so here I split x and y separately. Train test split is accustomed to having to split multiple things, and so here I can provide both x and y at the same time, and then the output will now be a tuple of length 4. It's going to split x into x train, x test, and it'll split y into y train and y test. And so this is actually a very common kind of line that you might see in machine learning projects. You'll see a train test split, and then just gets unpacked into 4 things. And this is going to just have the same exact kind of splits that we have. 4, 4, 0, 3, 1, 7, 8, 5, and then 2, 9, 6, and then it splits the x into that, and then it splits the y into that. Okay. You can also stratify. You can have it do a stratified split. Okay. So with a stratified split, so in our case, I've got z, where half of my values are zeros and half of my values are 1. And here I'm going to say split x and z. And here I want 40% of my values to go into my test case. So out of the 10 rows, 4 of them will end up in the test set. And here I'm going to say stratify on z. And so this will ensure that because overall half of my values are zeros and half of my values are 1, it's going to ensure that overall half of the values in the test set are zeros and half are 1s, and same is true for kind of the corresponding x rows. So as far as the test set goes, indeed I have 2 1s and 2 zeros, and in the training I have 3 1s and 3 zeros. All right, and I can specify different random states, and it'll kind of try to make sure that it maintains, 2 1s and 2 zeros in the test set. Okay, because I'm stratifying on z. Whereas if I remove this argument for stratify z, okay, so if I remove that, then there's no guarantee that we're going to get an even split. Now I have 1 1 and 3 zeros in the test set. Here I got it 2 and 2. Here I have 1 and 3 again. Okay, so that happens. Okay, yeah, question.
Could you explain this one more time? Why you would want to have 2 different sets, a training and a testing set?
So, an important thing in machine learning is to measure its performance on data that it hasn't seen. Because basically you train your model, and now you say, okay, I got a pretty good model, and we want to kind of have it make predictions, right? And the thing is when it comes to training your data or training your model, you can always make your model more and more and more and more complicated. And if you make your model more and more complicated, you can eke out better performance. Okay, so for example, a very simple model. Let's say we have children and we want to figure out their heights. A simple model could just be like, okay, every starting in 1st grade through 5th grade or whatever, we'll say every year we're going to predict. I don't know how much kids grow each year, but let's say we're going to predict their height goes up by 1.5 inches or something like that. Okay, very simple model, probably going to work decently well. Okay, And depending on the data, maybe you predict your slope goes from 1.5 to like 1.6 or 1.6 to 1.7 or something like that, right? Depending on your data. You can make your model more and more complicated, right? But if you have that, you can say like, well, I have these two kids, they're both age and the same grade, but they're different heights, and we're not getting great performance here because we're getting error. And you can say, well, what other variables can I include? And you can say, okay, well, I also have the kids' names, and perhaps, and if everybody has a unique name, you could say, well, okay, if the kid is 8 and their name is John, then we're going to predict their height to be exactly, I don't know, 4 foot 2 inches. Okay, and if the kid is 8 and their name is Matthew, we're going to predict their height to be exactly 3 foot 10 inches or something like that. Okay, and then you can now have zero error, right? And you're perfectly predicting everybody's height in your training data. But when it comes time to generalize, now you go out and you get new data, and here comes another kid, 8 years old, named Matthew, and you say, well, on the old model, when I predicted 3 foot 10 or whatever, I got it perfectly right, okay? And then you look at this and you go, oh, actually, this is no longer performing well because this kid who's 8 named Matthew is a different height. So if you overemphasize minimizing the errors on the training, you might start including additional variables. All right, this is an extreme case where we're using the name, but you might start including extra variables that actually didn't really make a huge difference. That just happens to have some weird correlation just particular to this particular data set. Yeah, question?
So just to make sure, so in the one with the x underscore train, x underscore testing, the train underscore testing, you're splitting x into 2 parts, x train and x testing. 75% of the data in x is the training sample.
Mm-hmm. Yeah.
It predicts 25% of the other x.
Yeah, so it's going to take your x, all of your available x values, and it's going to partition it. And here I said, I want around 25% to go into my test set, and it's going to take the other 75% and put it in my training set. And so we're going to use the training set to figure out what slope and intercept and what variables I should be using, or how complicated my model should be. I use that, and then I evaluate its performance on the test set. Okay, all right.
Which 75% is the Is it from 1 to, let's say?
No, it randomly selects them. So the only time you'd want to go sequential is in a time series. So for time series data, you would kind of want to use the first 75% and see if you can predict the last 25% in time series data. But outside of time series, you generally just want to pick randomly 75% of the rows, and randomly the other 25% goes in the test set. And that's just because if there's any kind of trends or patterns that are related to the row number, you don't want that to be part of your model by accident here. Okay, let me give you your next view quiz answer. We got to. Okay, so here I'm going to load up this data set called iron slag. This is like an old data set, and basically it was kind of just like figuring out the I guess like in the metallurgy process, like if you're some metal smelting factory, like in, I don't know, like you imagine like in Pittsburgh you have these steel factories. I don't know, do they still make steel in Pittsburgh? I don't know, you have the Steelers, but anyway, the data was the idea that you could kind of try to measure the iron content of this stuff that's being produced and stuff. And you can run a chemical test, but the chemical test is expensive. There's a cheaper magnetic test that you could run, and we want to see if can we predict the chemical results based on the magnetic results? And there's correlation, but it's not perfect either, right? So here I'm plotting the magnetic values versus the chemical values, and we see, you know, there's correlation, but it's not perfect, right? So what I'm going to do is I'm going to split this into train and test, and we're going to take our observations and we're going to just set aside 1/5 of it to be in my test set, okay? So these are the random rows that got selected for training. These are the random rows that got selected in the test, okay? So here, I'm going to just plot the training data, which is a subset of this. So they look very similar, this plot and this plot, except this one is missing around 1/5 of the data. And so we're going to try fitting a couple different models to the training data, right? So we're going to take the magnetic values, and we're going to say that's my X matrix, and then we're going to take the chemical values, and we'll say those are the response values. And the idea here is, can I accurately predict the chemical values based on the cheaper magnetic test? Okay, because we want to be able to get chemical values, but that chemical test is more expensive. So we want to say, like, if I run the cheaper magnetic test and I just do a couple operations on it, can I make good predictions about the chemical one? All right. Overall, there's a linear correlation of around 0.708, right? And if we do a R-squared value, you know, if we just did a straight linear regression, we would be able to explain around 50% of the variation in Y based on X. Okay, so the simplest thing we can do is just fit a linear regression model. I showed you how to fit linear regression using stats models. This would be linear regression using scikit-learn, and so here you establish a linear regression model in scikit-learn using linear regression. Yeah, question.
Sorry, I didn't quite understand the reshape part. Like, why did the reshape X?
Oh, okay. So one thing about the nature of scikit-learn is it's always expecting X to be a two-dimensional matrix, okay? And so here, if I just took train chemical magnetic values, it would be a one-dimensional array. Like for Y, it's just a length 42 array of one dimension, okay? One thing about scikit-learn is it's always expecting X to be two-dimensional. So even if you only have one column, you need to make sure it's 42 by 1. And so that's what I'm doing. I'm saying reshape it so that it's in one column, and I didn't actually know how many rows were in it. So I could have done reshape 42 by 1 if I knew how many rows were in X.
Oh.
But you can leave in the -1, which says, NumPy, you figure this out, okay? You figure out how many rows are necessary. And so -1 is just kind of like, I know I want one column, I don't know how many rows I need, so the -1 just says, hey, you figure it out, okay? So it produces a 42 by 1, which is now a two-dimensional thing, and not just a length 42 thing. All right, so here I'm going to establish a linear regression model. We're going to fit the model to our data. And this is, it just says, hey, I've got this linear regression model. We want to score the model. And this, we can see, oh, that's just the same as our R-squared value. Can I make predictions for the values 10 through 40? And we can kind of plot this, and this is the fitted line here. So how does cross-validation works? Okay, well, we're gonna just take this kind of the available data here. This is my training data, and I'm going to I'm gonna do 5 splits here, okay? And here we're gonna try fitting this on these different kind of things, and we get all of these different cross-validation scores: 0.58, 0.53, 0.45, 0.1369, 0.653. You know, 0.1369 seems worryingly low, but the average overall is 0.471. okay, what's happening there? What do those numbers even mean? I guess in the interest of time, I'm not going to bother explaining all of this code that I wrote here. Okay, here is the idea. All right, so this is all of the data I have in my training. Remember, what we're going to do is we're going to help us pick a model, we're going to take our training data and further split that into a training and a validation set. So what's going to happen is I'm going to take these available 42 data points and I'm going to subset from here. So you can kind of see this triangle of points ends up kind of missing out of here, but they end up showing up down here. Okay. What we're going to have is this is my, in cross-validation, we're going to use some points over here to fit this line. This red line is the best line that fits these purple dots here, or blue dots there. And then, using that same exact line, I come over here and I say, how well does it predict these dots? And you know, if I tried to fit it to the green line, I would have gotten a different line. But overall here, we say, oh, you know what, it does a decent job. You know, these maybe a few more residuals here. But overall, its R-squared value is 0.58, so not too bad, okay? Here is kind of a different random set gets selected in the for the test case. So again, if you were to take the blue dots and the green dots and add them together, you would get the original kind of data here, right? But when you do kind of cross-validation, you don't actually know which ones are going to be. So you look at the blue dots and you get a slightly different red line. Okay, so if you look at the red line up here and this red line here, you can see the slope is a little bit different, right? The slope and intercept are a little bit different, right? Here, you know, it's around 1014. And here, if you look at the 10, it's up at 15. Okay, and if you look at the angle of the slope, this one's you know, at 40, it's at like 31 over here, and then down here at 40, it's a little bit higher. I mean, maybe around 31 as well. So slightly different red line. Okay, but this is the best fitting line for these blue dots. And then we say, well, how well does it perform on the green dots that we left out? And here it also does fairly decent, okay? 0.53 is the score. Here is another set, all right? Different random kind of holdout set, and we say, all right, perform on this. So this is, again, slightly different red line. They all look kind of similar, but slightly different red line. How does it perform on the remaining green dots? We get that. For this one, okay, we said fit it on these blue dots. This is the best performing red line for the blue dots. How well does it perform on the green dots? And over here, on the green dots, it actually doesn't do a very good job predicting, right? So the flat green line is just what would have happened if you just predicted the mean. And predicting the mean for the green dots over here is not that much worse than just predicting this red line here, okay? And so all of these things give us different kind of scores here, and the cross-validation thing takes the average of all of them. Oh, I've run out of time, but I just want to show you one more thing. All right, so here's question 3 is A. That's going to be your final answer here. So we could try fitting, say, like a quadratic thing, okay? So again, you're trying to fit the best line to the blue dots that you have. So this is the best quadratic line that we have for the blue dots. And when we run it on the green dots, we can see, oh, you know what, actually doesn't do a good job because it does a bad job of predicting this point, okay? We get a wildly different quadratic fit for these blue dots, okay? But this one actually performs decently. This one performs a little bit better. Here's a different set of blue dots and green dots. How well does this quadratic fit? Okay, this is the best line that fits to the blue dots. How well does it fit on the green dots? Not so great. this is the best line that fits to these blue dots. How well does it fit on these green dots? This actually performs worse than predicting just the same dot for everybody or same value for everybody. We actually get a negative score there. Okay, how well does this one? This is the best quadratic line that fits these data. How well does it predict this? And it actually does a decent job here. But again, depending on how your random data is split, you can actually get better or worse performance here, right? And I tried it with higher degree polynomials, but we've run out of time. But you can kind of just take a look and see this concept of cross-validation in terms of fitting the best line to a certain set, and then you test how well does it perform on the data that you left out. Okay, we'll go ahead and wrap it up there. Sorry for going over, and we'll see you guys on Friday.